Alrighty then, I'm going to try to make a video answer key to the Energy Skate Park worksheet. So we have our Energy Skate Park here, we have our skater, we have our bars open, we get our skater going, we watch him go back and forth. Let's hope this works. All right, I can switch back to my worksheet here, and it asks what type of energy are at the skate park. Well, let's go back and take a look. It says kinetic and potential, and then thermal, although, right now thermal's not doing anything. So I'm going to put kinetic. And then it did say potential, but I don't love potential. That's potential energy based on gravity, so it's gravitational potential energy. And presumably there's going to be some thermal. We haven't seen it yet, but I'll put it anyway because it's in there. Maybe it'll show up. What are 3 ways you can change the total energy of the skater? Well, let's see here. I'm going to try to grab my skater. And I notice, first of all, when I lift the skater up, oh, there's the thermal, their total energy increases the higher they are. So that's one way. Let's go back here and type height above ground. What's another way? I asked for 3 ways. So let's presume, well, I'm going to pause this thing so they actually stay up in the air. Let's mess with some things. Let's try gravity. Oh, look at that. Now, gravity does change their total energy. And, so does mass. So let's go back here. Height above ground. I'll say force of gravity. And mass of skater. All right, why do you think there's a place on the energy graph for thermal energy? Well, I didn't see thermal energy yet, except when I drop the skater. What happens? There's an impact. So I'm guessing it has something to do with impacts at this point. Maybe I'll put that, maybe impact. We don't know yet. We'll find out. Maybe you know already. All right, fill out the bar graph for the positions indicated above. To modify a drawing, double-click on it. In the drawing mode, you can click on a bar and change its height. So on, the key being double-click on it. I'm going to put my skater, I think this thing is still paused. Nope, it's not. I'm going to pause it. Let's set my skater up there at position 1. I'm going to look, well, no kinetic energy, and all the energy is potential energy. So I go in here, I'm looking at this. Well, the total energy bar is all the way to the top. My total energy bar didn't really seem to be that tall, but it's actually true. We could leave it either way. I'm going to lower it down to put it here. And that's 1, 2, 3, 4, 5. That may come to bite me in the butt. No kinetic energy. I'm going to shrink that one right on down to, can't shrink it down to nothing. I guess you can shrink it down to nearly nothing. What happens? There we go. And I'm going to bring this one all the way up there. I guess I could, for the moment, I could just delete that. There. That shows me position 1, pretty much. All right, I'm going to start it and try to pause at position 2. Whoop, I kind of missed. Let's try it again. You'll notice we have to actually do it while the simulations are running. You can't just put them at position 2. All right, that's pretty good. We can see kinetic and potential are pretty equal. And the total energy hasn't changed. So I'm going to bring that up, put it there. And what we should be aware of is that the potential and the kinetic should about add up. If I take this green bar, the blue bar, and I stack them up, they should be as tall as the total energy. because the sum of those two gives me the total energy. Well, I'll do that. There, look at that. It's got a little more kinetic than potential, and that's fine. But when I stack them up, they do, maybe a little tall there. Let's bring it back down here. Got to make sure you do it right. There's some, some snapping and stuff. These things jump to places, but they don't always get exactly where you think they're gonna. So I'm gonna try to make it look good. Oh, right there. Okay, yeah. Now if I stack those two, kinetic and potential, they do add up to the total energy. They're each about half of the total energy right there. All right, position 3, here we come. Whoop. Okay, it's pretty much all kinetic, a tiny bit of potential. I'm gonna double click on here. Total hasn't changed. Whatever it was, whatever I decided to set it at to begin with, I gotta set it there again. The potential energy, I'm going to bring that right on down. There was a tiny bit. I could be cool and stack the kinetic on top and make it exactly the right height and then put it back where I found it like that. Except I don't think, yep, it's still not quite in the right place. There we go. Beautiful. All right, close that. Now we got all potential, half kinetic, half potential, pretty much all kinetic. And then, you know what? 4 and 5 are going to look pretty much just like 1 and 2. I'm going to cheat. I'm going to cut these two out. I'm going to copy and paste 1 and 2 in for 4 and 5. I'm not going to tell you how to do that because you know what? I'm doing this quick. I don't want to go too, I want to go fast, but you guys can do the right way. So this is pretty much what this first part should look like. How does the simulation model the real world? Well, there are skate parks. What else? Let's think physics. It shows the potential energy of gravity and how that becomes kinetic energy when someone goes down a ramp. Those are some things. You may have other answers. You know what? This is really not something that has like clear-cut right and wrong answers. Use your imagination. What else does this do to model the real world? How is it not like the real world? So far, a real skateboarder would stop. Would come to a stop. That's the biggest one I can think of. There's other things, I'm sure. Real skateboarders don't behave like that. Oh man, look at the big blank space that created. Oh well. Consider the energy of the skater. Does the amount of energy they have change over time? Describe how it does or doesn't. Now, I wasn't entirely clear here, but the total energy doesn't change, right? And that's really what I'm getting at. The type of energy does change. Part B, does the type of energy they have change over time? Yeah. The type does. The gravitational potential energy becomes kinetic, which then turns back into I'm going to shorten things. Gravitational potential. Oops, dang it, I'm just messing things up here. gravitational potential energy as the skater goes down the ramp and up the other side. And then it asks, describe the change. Well, I described the change. Refer to the different energy charts. The bars representing grav. I hate it the way it capitalizes potential. Come on. Energy. That capital, it just drives me nuts. Representing gravitational potential energy. Oh, the E gets capitalized. Dang it. It doesn't need a period, but it does it again. Nuts to you. The bar is representing gravitational potential energy. I guess it's the bar representing gravitational potential energy gets smaller going down the ramp, and kinetic gets correspondingly bigger. Yeah, gets bigger. The two add up to the total energy. There we go. Sorry, this may not be the best way to do this, but that's too bad. All right, reset the simulation. We're going to put our friction slider in the middle. We're asked, what types of energy, what types of energy are there now? Well, whoop, good God, it really messes things up when you do that. Huh. Okay, what types of energy are there now? There's, let's see, gravity. Oh, look, it's going to spell it for me. Energy. There's kinetic, and there's thermal. Yeah, let's take a look at this. I'm going to give us middle of the range friction. I'm going to put the skater up here. I'm going to play it. And you'll see, the idea here is that, friction is acting on the skateboarder, and most of friction really is heat. It does dissipate into the environment, so it doesn't build up the way it kind of shows this bar getting bigger and bigger and bigger. You'd think they're going to burst into flames, but that's not really how it works. We know that. But friction really does generate heat, as you know from doing this kind of thing. Warm palms. All right, so why do you think friction appears as thermal energy? Why does it appear as thermal energy? Well, friction generates heat. Friction generates heat. The molecules, the interaction of the molecules as things rub together, kind of, gets them all worked up, gets them vibrating, and that's heat. We can go into it more, but that's my answer. Sorry, I'm a hard time talking and typing at the same time. The molecular interaction of quickly moving surfaces causes vibration in the surface molecules. That's really what's going on. All right. Oh man, I really messed up my page, but that's okay. The stuff is still the same. Right. And we've got our skateboarder at the top, ready to go down. We know what this bar looks like. Keep it in mind. We're going to pause this thing as the skater goes down a little bit. Burp, right there. Okay, we've gained a little bit of thermal. So kinetic potential are pretty similar. Thermal, tiny bits gained. So let's go in here. Remember, this first one is actually for the beginning situation where we have no kinetic energy and no thermal energy. And this time we do something a little different with this. I'm going to raise it all the way to the top because our total energy is just our total energy. There's no numbers here telling us how tall that thing's supposed to be. So bring it all the way up. If you don't, we know there's a key thing we got to do, which is the 3 bars should stack up to the total height of the total bar. So remember the thermal energy was really tiny, like burp, 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 like that. And well, let me see. I guess I had a little more potential than kinetic still. So let's bring this up to about halfway, exactly halfway in this case, and our thermal or our kinetic up almost halfway. Let me just check here. I'm gonna stack them up. All right. All right. Oh, they don't quite reach. So let's make our thermal a little bit taller. Now they all add up to the total. Let's put them back where they belong. So there and whoa, there we go. Except, yep, there we go. Perfect. All right. We got to go check out position 3 down at the bottom. Okay. Very little gravitational potential, much kinetic, and more thermal. So let's go into position 3. Lift this guy up to the top. I'm going to leave the thermal about where it is. We've got almost none of this. I'm going to bring that right on down. And that means that most of our energy is here. Let's say like there. Let's try stacking them up and see how it goes. Whoop, that was the wrong thing to move. So was that. I don't know if I can move it. Too hard to move. We'll call it good. It looks pretty good. We don't need to be exact. All right. Let's go back to our energy skate park here and whoop. Okay. I might have missed position 4 a little bit, but we still got some kinetic. We got more potential and more thermal. There's even more thermal than kinetic right now. So let's go in here. I'm going to bring up my total energy all the way to the top. I'm going to bring up my thermal energy a little bit. And remember, most of it now is gravitational potential. I think I got big enough boxes to actually move these things. So I can put that there. I'm going to make it mostly that. There we go. Look at that. 3 add up. Let's put them back there. And Google does such a nice job of making things fall into place. All right. Yeah, it's fine. All right. And all the way to the top. Oh, look at that. They were pretty much at the top for that one. Sheesh. They didn't even make it. Huh. Well, you know what? Let's just get rid of this one. Whew. You know, you might have something more like position 2 here. Kind of the top of this chart fell off, but you might have position something more like position 2 for position 4, as long as you can see this increase in thermal energy. All right. What effect does turning friction on have on the simulation? What form of energy does the skater end up with? So, friction causes the skater to slow down, I suppose, and lose the, well, they're not really losing energy, but it causes them to slow down. They are losing that sort of momentum that they had. Let's say that. Lose momentum. How does changing the skater's mass change the simulation? Yeah, all right. I guess that's all I asked about that. How does changing the skater's mass change the simulation? Well, let's give them lots of mass. They get more energy with more mass. Huh. You go once, twice back to the beginning. This is our like fourth now cycle, fifth. Let's see. Let's give them tiny mass and see if they really move much differently. And go. Whee! There's return, 2 returns, 3 returns, 4. You know what I think? Doesn't really seem like much changes except the total energy. They seem to go about the same speed. In fact, I can look at their speed here. Let's see. Let's do it again. This person, what's the fastest they go? Oh, about 11 meters per second. It's about as fast as they go at the bottom there. And let's bring up their mass all the way to the top. See if we can get a sense of, do they go any faster? All right, keep an eye on that speedometer. I don't think so. They reached about almost 11. So how does changing the skater's mass change the simulation? Very little, I'd say. What about their energy? Well, more mass. Here's a little trick. You type in 2 dashes, and that thing turns it into an arrow. More gravitational potential energy. Kind of weird, though, that even though they have more energy, they don't go any faster in the end. I wonder what that's all about. You should look into it. Turn on the pie chart and the bar chart. How are they related? Does one give information which the other doesn't? All right, get rid of the speed, turn on the pie chart. I'm gonna turn off friction just to simplify the look of things and bring their mass down to about halfway. All right, so we'll start it up. And, well, here's the thing I'm gonna try. Remember I said that changing their mass changes the total energy. So does the pie look any different? The bar gets bigger. They've given them all the mass. Same thing happens in the pie. The bar chart keeps doing the thing it does. I'm going to take all the mass away, make them as small as I can. Okay, so the way that they're showing that there's less total energy is by changing the size of the pie. A small pie is small total energy. What do you think? Does one give information the other doesn't? How are they related? They show the same energies. They give the same information. The pie shows total energy by its overall size. So I think they give the same amount of information. Maybe you've seen something I haven't, but I'm going to say they give the same information. All right, go to the playground screen of the simulation, create some ramps. Can you make a jump? Can you make a jump which works in both directions? How about a loop? Well, I'm not going to make one for you. Have fun with that. Show it to me. And hope you enjoyed this. Looks like I got to move myself. All right. Enjoy. Fill out your worksheet, hand it in. I'll see you in class.